A very good day to all the students. Today we are going to start a new chapter, Chapter 4, on the separation process simulation. So Chapter 4 will be split into 3 sections. So first section is on the shortcut method. Second section is on the rigorous method, while the third section is on the extraction column simulation. So as of today, we are going to have the first section, which is on the simulation using shortcut method. So upon the completion of this lesson, students should be able to first describe the capabilities and also the limitation of the shortcut methods like distill or the STWU by knowing the method implemented and associated assumption in these models. Secondly, students should be able to configure a shortcut model like distill and the STWU block and review the simulation results. So before we go to the process simulation using X1 Plus, let's go through some common terminology of distillation column. So in distillation, a feed mixture of 2 or more components with different volatilities. So in this case, meaning that with different boiling point, is to be separated into 2 or more products. So typically, for a distillation column, we will have an overhead distillate and also a bottom product, in which the composition of these products are different from those in the feed by the application and removal of heat. So most often the feed is it can be in liquid or it can be a vapor liquid mixture. In the bottom product typically is in liquid form, but for distillate it can be in liquid, vapor, or a combination of both. For your information, distillation is a very energy intensive technique. When we want to use it, we have to ensure that the relative volatilities of the key component in the mixture is more than 1.5 to ensure the economic viability of the process. This is a very simple setup to enable the distillation to happen. So we have a mixture of water and ethanol, and we heat it up initially. So when the temperature reaches 78 degrees C, the more volatile component, the ethanol, will start evaporating, and the vapor will then cool and condense through the condenser. And when the temperature reaches 100 degrees C, the boiling point of the less volatile component, water, then the water will start evaporating and the vapor will then cool and condense through the condenser as well. There are different types of continuous distillation column. So we have binary column, which the feeds contain only 2 components. Multiple component column, in which the feed contains more than 2 components. Other than that, we have multi-product column, extractive distillation column, and also azeotropic distillation column. So if you look at extractive distillation and also azeotropic distillation, an additional feed is required to enhance the separation. Our focus in this particular chapter will be on binary column and also multi-component column. For azeotrope, it is actually denoting a mixture of 2 or more components where the equilibrium vapor and liquid compositions are equal at a given temperature and pressure, meaning that the vapor is actually having the same composition as the liquid, and the mixture, this azeotrope mixture, will actually boil at a temperature other than the boiling point of the pure component. For example, we are having an azeotrope of water and propanol. If we are having this mixture and we try to push it to a distillation column for separation, we are able to get the pure water as the bottom product, but we are unable to get the pure propanol as the top product. What we will get as the top product is the azeotrope with the composition of about 70% of propanol and the balance of water. In this case, we are not able to use the typical distillation column for the separation, but we have to shift to azeotropic distillation, a more special distillation column to ensure the separation happen accordingly to get the pure component. The main components of distillation column, I think one of the major one would be a vertical shell, where the separation of liquid components is carried out, and the column internal is normally located here. It can be trays, plates, or even packing to enhance the component separation. Other than the vertical shell, we are having a reboiler at the bottom of the column to provide the necessary vaporization for the distillation process. And we have a condenser at the top of the column to cool and condense the vapor leaving the top of the column. After condenser, we are having a reflux drum to hold the condensed vapor from the top of the column so that the liquid can be recycled back to the column as reflux. And as I mentioned earlier, we are having the tray or pack as the column internal to enhance the component separation in the column. These are some basic distillation terms. Based on the diagram given on your right, so we have feed here. So the feed stream is usually feeding into the column at the middle of the column. Then the tray that we introduce feed, we call it feed tray. And the section above the feed, we call it rectifying section or enriching section. A section below the feed, we call it stripping section. So we have a bottom product, distillate product, or we call it overhead product. So as I mentioned just now, we are having reflux here. Reflux is basically a portion of the overhead liquid product that is being recycled back to the column for the cooling purposes or for the condensation of the upflowing vapor to enhance the separation efficiency. So the reflux is over here. So we are also knowing that the more reflux we put, then we are able to enhance the column separation. And at the same time, we can actually reduce the number of theoretical stages required in the column. Whenever we have binary feed, which is involving two components, we will use Mercaptil method to determine the number of stages. Okay. And the diagram given here is indicating the Mercaptil method. Is a graphical method for us to identify the number of stages required for a binary feed. When we have multi-component feed, where the feed is involving more than two components, then we will normally use several shortcut methods here. There are Wien method, Underwood method, and also Chilean method. Okay. And you can, of course, adopting this method and solve the equation manually to get the required parameters like minimum number of stages and also minimum reflux ratio as you learn in unit operation. But as in PSCAD, you can actually use Expand Plus, uh, typically shortcut method, that adopting the same method here to solve the problem. So light key and heavy key in multi-component mixture. Um, Later on, when you use the shortcut model in Expand Plus, you may need to identify the product recovery of light key and heavy key. That's why it's very important for you to know what is light key and what is heavy key. Light key is a more volatile component, and heavy key is a less volatile component. If you are having multiple components in the mixture, first you have to list it down in the ascending order of the boiling point, meaning you have to first list down the component with the lowest boiling point and followed by the component with higher boiling point. So if you look at the example given here, propane is with the lowest boiling point, while N-pentane is with the highest boiling point. Okay. And of course, if we put this in a distillation column, we are able to get the top product, which is dominantly or with the dominant product of propane, okay, which is with the lowest boiling point here. Then that is our light key. And in the top product also, you may have a little bit of heavy key, like iButane. So in this case, if we draw a line in between propane and iButane, then we can identify propane as light key and iButane as heavy key. So it is always confusing to the students about product purity and also product recovery. Okay. I've given an example over here, adopting the example given in the previous slide by giving you the top product composition in terms of molar flow rate, the feed composition in terms of molar flow rate, and also the bottom product composition in terms of molar flow rate. So in order to determine the propane recovery in the top product, as propane is our light key, the equation that we have to use is molar flow rate of propane in the top product over the molar flow rate of the propane in the feed. So in this case, we just substitute the information given. So we have the molar flow rate of propane in the top product is 99 mole per hour, while the propane flow rate in the feed is 100 mole per hour. So if we substitute the value and calculate accordingly, the product recovery for propane in the top product is 99%. While for propane purity, we have to use the equation of molar flow rate of propane in top product over the total molar flow rate of top product. So in this case, we are dividing 99 by 101.4, and we are getting propane purity in the top product as 97.6. So bear in mind, propane recovery is different from propane purity in the top product. So you can use the same equation to calculate the heavy key recovery in the bottom product. So it's the same equation. So before we proceed to the next session, focusing on using the shortcut model in Expand Plus, we take a break first. Thank you very much.